Hi everyone, we are Akihiro Suda from NTT and Wei Fu from Alibaba Cloud. This session will dive into the design of functionality and the new features in the upcoming version 1.4 release and how to exchange functionality with plugins. The first topic is the overview of functionality. Functionality is a container runtime implementation that can be used by high-level container engines such as Docker and Kubernetes. But functionality itself doesn't create containers. Instead, it relies on lower-level runtimes such as runc, gvisor, or kata containers to create containers. So functionality is often called as mid-level runtime in comparison with high-level runtime such as Docker and low-level runtime such as runc. As a mid-level runtime, functionality is often compared with CRI-O, which is another implementation of mid-level runtime. But CRI-O is not extensible as functionality, and CRI-O rather puts more focus on CRI API. So what does functionality actually do? It provides APIs for managing container processes, container images, file system snapshots, and relevant metadata. The API is available in both of CRI API used by Kubernetes and Container Native API, which is used by Docker. Functionality is one of CNCF graduate projects, as in Kubernetes, Prometheus, Envoy, and Kubernetes. Functionality has open governance model, and we have maintainers from several companies, including Apple, Docker, Google, IBM, and Microsoft, as well as NTT and Alibaba Cloud. This figure shows the architecture of functionality. You can see several core services, such as container service and image service, in the middle of the slide. And you can also see several backend subsystems, such as runtimes and file system snapshotters. These subsystems can be easily extended with plugins. We have support for runtime plugins such as runc and gvisor, and snapshot plugins such as overlayfs and butterfs. And also we have content store plugins and stream processor plugins. My co-speaker Wei Fu will take a deeper look at these plugins later. The next slide shows the adoption status of functionality. Functionality is adopted by container engines such as Docker, and also by several Kubernetes distributions and managed Kubernetes service providers. Notably, functionality is adopted by all of Amazon EKS, Azure AKS, and Google GKE. And aside from Docker and Kubernetes, functionality is adopted by several projects, including BuildKit, which is a modern implementation of Docker build, and LinuxKit, a Linux distribution with functionality as the init process, and also FASD, a function as a service infrastructure for functionality. Functionality is also included in the latest release of VMware Fusion, and you can run functionality directly on macOS using the VMware's virtual machine technology. as a runtime plugin to run Linux containers on macOS. The next topic is about the upcoming features in Containerd 1.4, which is to be released this month. Containerd 1.4 comes with support for lazy pulling of images, which means running containers before completion of downloading the images from the registry. This is useful when your image contains a lot of extra files that aren't actually accessed. For example, Python images and Java images tend to contain a bunch of extra library files. With lazy pulling technology, you can skip downloading these extra files. For lazy pulling, we need to use new image formats such as StarGZ and eStarGZ. StarGZ is a variant of tarGZ format that allows seeking a specific offset in the archive. eStarGZ is similar to StarGZ, but it allows patching requests for frequently used files. This slide compares legacy tarGZ and StarGZ. With legacy tarGZ, you can't inspect file offsets without downloading and reading the entire archive. But with StarGZ, you can inspect the file offsets immediately right after reading the footer structure, because the footer structure contains offset information of all files. The next slide compares StarGZ and eStarGZ. eStarGZ profiles actual file access pattern and reorders file entries so that relevant files can be prefetched in a single HTTP request. So if you have a Python application in the container, the application script file, along with the Python interpreter /user/bin/python3 and dependencies such as libc.so are squashed together into a single chunk inside the image. This chart shows the startup latency of several containers such as Python and GCC with the legacy OCI format and StarGZ and eStarGZ. With eStarGZ, the startup latency can be significantly shortened. It's about 7 or 8 times faster compared to the legacy OCI format in the best case. The further detail of lazy pulling was presented yesterday. The slide deck is available at the URL shown in this screen. And Containerd 1.4 also comes with support for SE Linux MCS, which means multi-category security. With MCS, you can assign category identifier to container processes and data volumes. These category identifiers ensure separation across containers. So a container with category number 42 cannot access files that are associated with category number 43 because the category number is different. And Containerd 1.4 also brings support for cgroup version 2, which is a new cgroup hierarchy and already adopted by Fedora since Fedora 31. The cgroup version 2 has a simple directory layout compared to version 1, and also has a lot of features including eBPF integration Cgroup version 2 is also friendly to non-root users as it supports delegating cgroup permission to non-root users. And with cgroup version 2, we improved support for rootless mode, which means running containerd as a non-root user so as to protect the host from potential vulnerabilities. Rootless mode has been already adopted by several containerd-based projects, including Docker, BuildKit, and K3s. The rootless mode is also being proposed to the Kubernetes upstream as well. In Containerd 1.3, the rootless mode didn't support imposing resource limitations, as in Docker run dash CPUs and Docker run dash memory, because unprivileged users cannot control cgroups on cgroup version 1 hosts. And yet, Containerd 1.3 didn't support the overlay FS snapshot because of the limitation of the kernel. But Containerd 1.4 do not have these drawbacks. Containerd 1.4 supports resource limitation when the host is running with cgroup version 2 and with systemd. And it also provides overlay FS functionality by using fuse overlay FS, which is a user space implementation of overlay FS. Let me show the demo of rootless Kubernetes with Containerd on a cgroup version 2 host. This is called usernetes. My ID is 1002. This is not root, and I don't have access to sudo, so the sudo command fails. And as this user, I'm running Containerd process and kubelet process without the root privileges. So the ps command shows Containerd process and kubelet process running as the rootless user. And let's create a pod with cgroup resource limitation. The pod manifest contains limitation for CPU and memory. And the pod is now running. And inside of the shell, we execute cat sysfs cgroup CPU max and memory max. And we can confirm that the cgroup resource limitation is applied as expected without the root privileges. And Containerd 1.4 also comes with support for Windows CRI and other minor changes shown in this slide. Please refer to the release note for the further information of these changes. The last topic from me is planning of Containerd 1.5. 1.5 will support NRI, Node Resource Interface. It's a new common interface for controlling node resources, such as cgroup, in the same manner as CNI. And 1.5 will also support API for managing pod sandboxes as first-class objects. We are also discussing the support for file system quota toward version 1.5. That's all from me. The next speaker is Wei Fu from Alibaba Cloud.
Hello everyone, thanks for joining me today. My name is Wei Fu from Alibaba Cloud. I also be a Kubernetes maintainer. My topic is Kubernetes external plugins. In this talk, we will talk about how to integrate it with Kubernetes by its very powerful extensibility. Before we get into the detail, let's recap the architecture. Look at this picture. Kubernetes exports very more gRPC service for the internal component, like container service, content service, div service, and so on. The internal components maintain a very low-level resources, so that those API is very general purpose. The developer can assemble those components together in a variety of ways to build any kind of functionality on the client side. And the Kubernetes also provide a very useful client library to have to do the adoption. It is all about the client side extensibility, but it is good enough. There are always requirements about changing the backend. For example, the user wants to use the new compression algorithm for the image layer data. So they need the Kubernetes to handle the new media type of image. And also, the user wants to use the very special file system for the image storage to integrate it with like runtime. So you might ask one question. If the community doesn't accept my proposal about changing the backend, do I have to fork the repo and go along? The answer is no. Kubernetes care more about the interface design, so they know how to work with your very special backend implementation to handle the container lifecycle and image data. So you don't need to fork the repo, you don't need to do the hacking thing. Just add some configuration, the Kubernetes will know how to use your very special backend implementation. We call it external plugin mechanism. There are three kinds of the external plugins. One is the streaming processors. The second one is the gRPC privacy plugin. And the last one is the runtime V2 protocol. Let's go through one by one. First one is streaming processor. When you run a container, you have to put the image down and unpack it for the container root.fs. We know the image data has manifest, configure, and layer data. We know image layer data is packaging in the tar archive. For the distribution faster, the OSI spec allows the image builder to compress the image layer with the gzip and the z-standard. We know the z-standard is the new one, and the gzip is more common case. Look at this picture. When you download the image, the client will call the div service to read the image layer data to get the tar archive and then unpack into the snapshot. If the image layer is with the gzip compression, the Kubernetes will decompress it into the tar string before unpack. We know Kubernetes only support gzip compression right now. So what if the user want to use the z-standard image data? So what if the user want to use the encrypted image data? At the beginning, Kubernetes integrated with the encrypted media type in the code base, but it is all about the implementation design rather than interface. It is not good enough for the other media type integration. So Kubernetes introduced the streaming processor binary plugin. This kind of binary plugin is intended to be a media type converter. When a new media type is detected by the streaming processor configuration, the Kubernetes will call the corresponding streaming processor to do the media type converter to get the tar archive streaming. The first adoption is image created. It is a subject is a sub-project of Kubernetes. It is used to encrypt the image data. I also bring a demo with this standard media type. Look at this configuration. He talked to the Kubernetes. When Kubernetes see this kind of the media type, please call the standard with the argument to get the tar cap. So let's check out the demo. So right now we have the Redis image in the gzip. So let's do the converter to get the standard data. Okay. Yeah, we can see the image layer data has been changed. So we push to the local registry. Yeah, and pull it and unpack it and see what happened next. Yeah, no surprise. Kubernetes doesn't support this standard right now. But we have the streaming processor. Yes, let's see the configuration. Yes, and append into the Kubernetes configuration and restart the Kubernetes server. And retry it. Yes, it was. So you can see with the field configuration, Kubernetes will handle any kind of the media type of the image data. We know we cannot just use the image layer data for the container. We need to unpack into this snapshot. Kubernetes provide a built-in snapshot plugins, and one very special is the privacy plugin. It is used to redirect the request to the remote external snapshot plugin. Like an internal snapshot plugin, the external plugin has to implement those API service so that the Kubernetes know how to communicate with your own server. Like a streaming processor, you just need to add some configuration to tell Kubernetes how to connect it to your server. That's very simple. So right now we have covered the streaming processor and the snapshot external plugin. But we know there are new generation OCI runtime implementation. For this case, Kubernetes will handle it by the runtime Wei Fu protocol. Before supporting runtime Wei Fu protocol, Kubernetes required the other runtime CLI to be like runC CLI. We know the runtime has their own abstraction. So the CLI approach will introduce the new issue with the containers data and the container resources management. We know each runtime has their own value. Kubernetes cannot just introduce the code into the code base. Kubernetes just need to focus on the protocol to know how to talk to each kind of runtime. So Kubernetes introduced the first class stream API for the runtime authors. So the runtime author can implement their own stream, like a gvisor, color container, and firecrack. Yeah. Runtime also need to implement those API service so that Kubernetes know how to talk to your server. And we know stream is the background long-running process. Before connecting to it, Kubernetes need to find it and start it. In order to make the integration easier, Kubernetes bring a binary name convention. For example, when you use io.kubernetes.runc.wei2 as stream name, Kubernetes will convert it to the binary name. It will call Kubernetes hyphen stream hyphen runc hyphen v2. So you will use the binary name and to find the binary path and start it. And someone will confuse about the name about between the runc.v1 and runc.v2. Both are the runtime v2 implementation, but runc v2 implementation has a more feature than runc.v1, like a grouping feature. One runc v2 stream can manage more than one container. It is very useful for Kubernetes case. One pod, one runc v2 stream. So you can save more CPU and memory resources. Right now, CRI plugin use runc.v2 as default runtime in the 1.4 release. And one more thing I want to mention here is the delete subcommand. It is used to clean up the resources created by stream. If your stream is unexpectedly killed, Kubernetes will call the delete command to clean up the leaking resources. So the runtime also needs to handle it very carefully. And we know Kubernetes stream right now is use the name pipe as default channel to export the container send output to the receiver, like a Docker and CI plugin. But we know it requires the receiver must be alive. If the receiver is down for some reason, and the container is still running and still output the logging data, the main pipe will be haunted, and then he impacts the running container. To fix this issue, the runtime v2 use URL schema to introduce the logging plugin, but by default, runtime v2 implementation must support the name pipe. So if the user look at this picture, if the user use the file as the schema, use the file name as the path, the Kubernetes stream will write the log data into the file directly. And if the binary is the schema, the Kubernetes stream will set up a background long-running process to handle the log, like a system log exporter. Those two schema are optional for the runtime author. And that's it. That is all my talk. And in this talk we know about how to integrate it with Kubernetes, right? So happy to see everyone to join me today, and see you next time. Goodbye.